to step that off.
Really? Who's that speaking to me?
Omar.
What why not?
I have no idea.
Yeah. I mean, I thought that only happened to old guys like me. Didn't get sleep. There are nights when I don't sleep either, but
I don't know. I just stay up on my computer, just reading.
Right.
Something else to do. I gotta be productive.
Well, yeah, but you do need some sleep. The body needs to turn.
I eventually get my rest, but I don't really sleep at night.
Really?
Yeah.
Okay. Well, try not to go to sleep during the class today.
No, I'm wide awake. I have a lot of energy. I have ADHD.
Sounds like it. Good morning, Jonathan.
Good morning.
How are things going over there in the mailroom?
It's fine, slow, but we had a flood here on campus.
That's what I hear. I wasn't here. So when you say a flood, I mean, how much of the campus was flooded?
What was the underground maintenance tunnel and the campus center basement, 250,000 gallons of water.
Oh my God.
Yeah. So if some buildings still have
200,000?
250,000 gallons of water.
Oh, hell.
And so where is that water now?
They've been pumping it out, so it's basically all over the ground. But that was Monday. Mm-hmm. So most of it's gone, but they're still trying to get power back up.
What happened? How did it happen?
An old chilled water pipe burst. And it was in the maintenance tunnel, and it flooded the tunnel and then rose up to the buildings.
Holy cow.
Yeah, so the AC is still down for some buildings. It's not really working well where I am. Yeah, it's been fun.
Oh my. Yeah, I'd heard about it. And they canceled those machine shop classes and stuff like that, or any classes, I guess, on campus. The few that were there.
Yeah, Tuesday they canceled everything, but they came back Wednesday.
Mm-hmm. Okay. Flood on campus, and there was still no rain. So it's kind of odd, but yeah. Oh, that's too bad. That's too bad. Jose Gonzalez. So we'll give it a couple more minutes. Let the sleepyheads get up.
Morning.
Who's that? Is that Angel? Anastasia, good morning.
Good morning. How are you?
I'm okay. Okay. I'm back. Elmer, Denise. Give it a couple more minutes. We have 18 students. I'd like to get that into the 20s before I start, but maybe we won't. We really should have twice that many. All right, good morning.
Morning.
Good morning, everybody. Wake up. Yeah. Okay, let's get started with what we've got. I was out of town, as I told you. I got back late last night. I did grade a couple of assignments, a couple of you last night and a few this morning. But there are more to grade, and that's good. That's good. And I will take care of that today and tomorrow. I should be caught up with everything by tomorrow. And it's not quite sure which, I can't really comment on what needs to be done with you because I don't know what you turned, basically what you turned in. But by all means, if you have completed all of the assignment for, you're behind, and so you need to do that. And again, I have a sheet here with the grades for some of you, but again, I haven't graded a lot, so you can say, well, I turned it in, and you probably have. There are 6 assignments in week 4, and most of you are doing quite well with those. The one where you have to calculate the voltage drop across the current limiting resistor, you must remember again that the voltage across that current limiting resistor is not the supply voltage. You must subtract the 2.2 volts for your LED from the supply voltage, and that's the voltage that's across the resistor, and that's the voltage that goes into the formula, the basic Ohm's law formula to find it. Most of you, vast majority of you, understood that and did that right, but there were a couple of you that I asked you to do it over again to take care of that. Other than that, I'm getting, by your grades that basically what's happening, and I like what I'm getting. And some of you have gone the extra mile, and you don't have to, but you have, and you've shown me pictures, and it's very nice work in turning in the assignments. So that's for week 4, and that, we're in week 5 now, and of course we're in the second Thursday. I mean, obviously we didn't have a Tuesday, so we'll get caught up now, and we'll look at week 5. So are there any questions about anything in week 4, those 6 assignments of week 4?
I had a question, Professor.
Yeah, who's that, Joseph?
No, this is Elmer.
Okay. Mm-hmm.
I did have trouble with the 10 LED pack.
Uh-huh.
When I set it up on my circuit list, the solderless circuit board, the breadboard, I probably was wiring it wrong, but it was heating up like a little bit too hot to the touch. But the lights were lighting up, but I wasn't getting different colors. So I'm assuming that I was probably setting it all up incorrectly.
Okay, all right. Let me comment on that if I may. A couple of things. You brought up something that's really quite interesting, and I haven't talked about it before, and that is the touch test. If you cannot keep your finger on anything that you're making because it's too hot, then there's something wrong, okay? And it is a good little test. People go around with a little finger and touch it. So definitely there's something wrong. And what's wrong, of course, is there's more current flowing through that device than there should be. And I suspect, again, if we were in class, this would be different. I suspect that the current limiting resistor you're supposed to use with those LEDs is not connected correctly in the circuit, and you're going directly from the 9 volts through to the LEDs. So again, look at the picture, look at the schematic now. That's the main thing. You have to go through that through that resistor to check out an LED. Now you have 10 separate LEDs there. Don't get panic about 10 LEDs. Just deal with one LED at a time. And just like any other LED, it's just an LED with a current limiting resistor across a 9-volt battery. That current limiting resistor should be anywhere from 100 to 1,000 ohms. If it's 1,000 ohms or something like that, there'll be less current. It won't be as bright. If it's 100 ohms, there'll be more. If you less than 100, it's going to be kind of dangerous for the LED. Some of you, most of you, almost all of you, have a bar of LEDs in which all the LEDs are the same color and they're red. Now, not everybody has that. So you may be getting different colors. And I graded one this morning where the student put down a number of different colors, which is kind of interesting. And that's okay. But for the most part, it should be red, one LED at a time. Go through the current limiting resistor. Don't short that current limiting resistor out. Don't put it in the holes so that they line up and you've in effect shorted the LED out. Again, I mean the resistor out. Again, oh boy, if we were here in class, I'd just walk over and I could see exactly what the problem is, or your neighbor could, and we could take care of it.
Yeah, I thought I was maybe doing something wrong because they were all red, and I think for that activity it asked what different colors I was getting. So I was like, oh man, maybe I'm doing something wrong here.
Yeah, no. The vast majority of cases, they'll all be red. Mm-hmm. So don't worry about that. You didn't do anything wrong if they're all red. You may have done anything wrong if they're different colors. Sometimes they'll change with different voltages, but no, it sounds like you're doing okay with that. Well, we've got 21 students. Good, we're in the 20s. All right, are there any other questions about any in 4? There was a lot to do. We had 6 exercises. You still have 6 exercises. And again, I haven't clamped down on late stuff yet. I mean, I want to give you the time to do this, but stay caught up. And again, I have a lot to grade yet, so I don't know where you're at. But by all means, if you haven't finished week 4, if there's still assignment or 2 or whatever out on 4, get that done today. Get that done. Because we're going on to 5, and there will be 3 assignments in 5 to do this week. Short ones, I think. So if we can, then let's take a look at week 5 here, Ohm's law. That's the main topic here. Not the only thing we're going to talk about, but it's really what it's all about. Let's see what I say here on read this first. Okay. Okay, so, all right. Well, you see these little triangles, which we'll get to shortly. But what am I saying here? Ohm's law is without a doubt the most significant law in all of electronics. Ohm's law, that's it. Everything else follows from that. The good news is Ohm's law is really very simple to work. It's extremely simple to work with mathematically. You can't get any easier than this. And it's very significant though. And what we want to do when we talk about Ohm's law today is we want to start out by trying to figure out, what is it saying? What is it saying? What does it mean, Ohm's law? What was Ohm saying? And then we'll do the math. Number 2, we'll do the math, but the math's so easy, you'll see. It's not just about solving the mathematical problems. I want you to get a sense of what it's all about. And simply stated, it tells us that the current are proportional. That means if you have more voltage, you'll have more current. If you have less voltage, you'll have less current. That's what the directionally directionally proportional means. It's straightforward. And it's intuitive. You know, yeah, you crank up the voltage on your power source, you're going to get more current. It also says, though, while the current and resistance are inversely proportional. In other words, the more resistance, the less current. The less resistance, the more current. And that's kind of intuitive too. So here's the real way, one way to look at it. It says, how do we control current in a circuit? How do we mess with it? How do we vary it or change it? And there are two ways. You can mess with the voltage, or you can mess with the resistance. And if you mess with the voltage, it means if you crank it up, you'll get more current. If you crank it down, you'll get less current. If you leave the voltage the same, you can also control the current by what you do with the resistance. More resistance, less current. Less resistance, more current. Most of the time in a circuit, we will mess with the resistance to affect the current rather than the voltage. We'll start a fixed voltage source like a 9-volt battery or a 12-volt source. And then if we want different amounts of current in different parts of the circuit, we change the resistance. Anyway, in use for over 200 years, it is as valid today with your smartphones as it is anything else. It's valid. It's valid in AC circuits, DC circuits. It's as valid today as before. Before we get into Ohm's law, we need to understand the metric numbering system. And you've had some exposure to that already, but we're definitely going to look at it in more detail now. So what's the bottom line here? This week, you will have 2 exercises and 1 activity. You're going to have 2 exercises we'll look at in 1 activity. The first exercise asks you to practice metric conversion. So I'll go over that with you. The second exercise, you will question Ohm's law and do some simple Ohm's law calculations. And in the activity, you will prove out Ohm's law by creating a simple circuit and measuring the current flow in it. It's very simple and straightforward. And the problem here is that you do not have, or I cannot assume that you have a variable power supply. A power supply is something you plug into the wall socket, changes AC to DC, and you get a DC out, direct current out at varying voltages, or fixed and varying voltages. And I assume you don't have one. If we were in class and in the lab, you'd have one in front of you. And so the activity that I would give you with Ohm's law would be more complicated than the one I'm giving you here. This one, as you'll see, just assumes you have a 9-volt battery and asks you to make 1 calculation and 1 measurement. So it's just something to do. It shouldn't take long. These are the triangles that are associated with Ohm's law, and these are the formulas. What Ohm's law says is that if you know one of the 3, you can find the other, back up. If you know 2 out of the, you can find this one. By we mean working circuit, current flowing I, and has some resistance. Every working circuit has that. And if you know 2 of those, you can find the 3rd one by using these equations or formulas. This one says V equals I times R. So what we're saying here is you go up here, V, and this is multiplication, V equals I times R. You put your finger over the V and you've got this. But the formulas are so simple, you can just remember them. V equals I times R. This one says that, look, if I know the voltage and resistance, I can find the current. I equals divided by R, V over R. And this one says, hey, if I know the voltage and the current, I can find the resistance. R equals V over I. You have to be working with the same units in each case. So if it's milliamperes, you will change it to amperes. If it's kilo ohms, you change it to ohms, that kind of thing. But if you watch that carefully, you can get this. Are there any thoughts on that? I'll go back. To convert before we get into the Ohm's law exercise. Okay, good. So here it is. It's worth 40 points. So look at it carefully. We're going to look at this for a moment. But basically, what we've got is this is divided into 2 or 3 parts. There's a video, or maybe 4. There is this chart, which you're going to, you need to print this out and have this in front of you. Well, you need to do that with the whole exercise, but this is the chart that you'll be looking at. And then there is a 3-step process in doing the conversion. If you follow the 3, don't try to short it, just go through the 3 steps, and you'll do that mentally, really. Then you'll get it every time. And I have 2 examples here to show you what to do. Then we go into the problems. And it looks like these came out goofy like that. You have 20 problems. We'll look at that in a moment. In electronics, we are customized to use, we generally use large and small numbers, or we do use large and small numbers. If you start out here with the base unit, at the chart, the ones, we go to kilo, we go to mega. Kilo means 1,000, mega means million, giga means billion, and tera means trillion. And we could keep going, but we don't really need to for our purposes. But we use these very large numbers. Look at how large they are. 1,000, 1 million, look at all the zeros. We also use very small numbers. If we go the other way, milli is 1,000, micro is 1 million, nano is 1 billion, and pico is 1 trillion. Look at all the look at the decimal point and all the zeros. Oftentimes, very often, we are asked to convert from one unit to the other. When we do that, we do not change anything. We don't change the value. We just change the way we express it. For example, again, with kilo, most of you were so familiar with kilo. If you had a salary that was being offered at 68K, and it said $68K, they would expect you to know that K means 1,000. So you'd have 68,000. You could write out 68,000, 68000 with 3 zeros, or you could put 68K. The only purpose here is to express it differently, eliminate the zeros. The point with all of this, though, is that as you go up the scale, you get larger. And down the scale, you get smaller in designation, If you're ever moving up, if you're here, if you're at micro and you move up here, milli is larger. You know, this is a smaller number than this one. And as you keep going up, you'll get larger. As you keep going down, you'll get smaller. So try to remember that. I'll show you these steps in a minute. Let's see what this video is. I haven't seen it in a while. I think the last time I wasn't all that impressed with it. Let me just see. Maybe we'll look at it. Maybe we won't. Here in class. Oh boy.
Okay, in this video, what I want to review is metric conversions. And there's a saying that'll help you if you can remember it. And there's a bunch of different sayings, but to remember the prefixes, I would come up with a saying or remember a saying like King Henry died by drinking chocolate milk. Sounds silly, but it'll help you hopefully remember those prefixes. So it's King Henry died by drinking chocolate milk. So here's what the letters would stand for. You have a K, King Henry died by drinking chocolate milk. Okay, so here's prefixes. The B here, we'll see, stands for what we say is the base unit. And that would be,
the one.
Depends on what we're measuring. That it could be grams, it could be liters, it could be meters. Okay, so what does this mean? These are the prefixes. This is kilo, this is hecto, this is deca. Okay,
so he's going to go into kilo, hecto, and we're not dealing with hecto, dealing with these here. Look at it to the extent that you can get something out of it. But the main thing here is the the chart. Okay. When you're confronted with a problem, there'll be 20 problems to work with. Converting from one metric designation to another, follow these 3 steps. And again, you'll be doing this mentally quick enough, but whatever it takes, follow the 3 steps. Number 1, ask, am I going from a smaller to a larger or a larger to a smaller designation? These are the designations. Am I being asked to convert micro to milli? Am I being asked to convert giga to kilo? Whatever. Larger, up, down, smaller. So you have to answer that first question in your mind. Am I going from to a larger or larger to a smaller? Then number 2, you say, what direction do I move the decimal point? And you're either going to move it to the left or to the right. You're not going to move it up or down. You're going to move it to the left or the right. And when converting from a larger to a smaller designation, you move it to the right. And somehow you need to remember that. From larger to smaller, you move it to the right. When converting from smaller to larger, you move it to the left. So those are your choices, right or left. And larger to smaller is right. Smaller to larger, is left. Then number 3, how far do you move it? And the key is you'll always be moving it in groups of 3. You'll either move it 3 places, 6 places, 9 places, 12 places, 15 places, whatever. You'll never move it 7 places. You'll never move it 2 places. You'll never move it 1 place or 5 places. You're always going to be moving in groups of 3. And every time you go up the chart, every time you go up or down the chart, 3 places. So if I went the units to kilo, I'd move it 3 places. If I went from units to mega, I'd move it 6 places. 3, 6, another 3, 6, giga 9, tera 12. So you'll always be moving from in groups of 3. So these are the 3 questions you ask yourself. Am I going from a smaller to a larger or larger to smaller designation? What direction do I move the decimal point and how far? And again, for every designation here, you move it 3 places. Here's an example. Convert 140 milliamperes to amperes. In other words, convert it to units. Units means it doesn't have any metric designation. There's no kilo, there's no mega, there's no micro or anything. It's just units, like $47,000. You write 47 and 3 zeros. So that's what it's asking you to do, convert 140 milliamps to amperes. You assume that the decimal point is right here. It's rarely written, but it's 140 milliamperes, thousandth of an ampere to amperes. Remember, you're not changing the value. It's the same amount of current flowing in the circuit. It's just you're changing the way you express it. Okay. So ask yourself, are you going from a smaller to a larger? You ask yourself that question, and the answer is you are going from a smaller to a larger designation. You're going from milli to units. Here you are, milli. You're going up to units here. So you're going from a smaller to a larger because you're going in the chart. Anytime you go up in the chart, you're going from smaller to larger. Okay, that answers the first question. Move the decimal point to the left. So you're going to go to the left. The decimal point, again, is understood to be right here at the 0 point here. You're going to move it to the left. How far do you move it? You move it 3 places because you're going undesignated here to here. That's 3. Every time you move 1, you go 3. So here it is. You move it 3 places to the left and you have 0.140 amperes. The 0 in front of the decimal point is a printing convention. It's used just to show you that so we don't lose the decimal point. It has no meaning, but there it is. In other words, and look at the equal sign. This is saying 140 milliamperes is the same thing, equal to the same thing as 0.140 amperes. It's just another way of expressing it. And for the time, you're going to definitely have to go back and forth like that. Let's look at number 2 as an example. 23 mega ohms. Convert it to ohms. That's what it's telling you to do. So it's telling you to go from mega to units. When I say ohms, not kilo ohms, not micro ohms, to ohms, that's units. So you're going from here to here. We've written it out as 23 mega ohms, but we want to see it in units. You are moving from a larger to a smaller designation. The decimal point is understood to be here. You're moving from a larger to a smaller. So you move the decimal point to the right. Move it to the right. And in this case, you move it 6 places because you're going 2 designations. You're going here, down to here would be 3, down to here would be another 3, so you have 6. And so there it is. Decimal point would actually be here. Should have written out there. There's 23 mega ohms. It's the same thing, equals same thing as 23 million ohms expressed with a bunch of zeros. Same thing. Are there any questions? When you do this, these three steps, excuse me, look at the examples, and then you go ahead and do things. Convert 0.18 milliamperes. I've written it out like that. Same thing here at this point. To microamperes. So you're going from a larger to a smaller designation. Work it out. Get it. Pretty sure you'll be fine with that. Down here, I'm sorry about this. I've asked you to do some adding. Do operations here. You must do it in the same units. For example, 15 says, what is the sum of 40 milliamperes and 6,880 microamperes? You can't add 40 to this number, 6880. You have to convert either the microamperes to milliamperes or the milliamperes to microamperes and then do the addition. Are there any questions about metric conversion? How many people do we have? We have 22. That's about what we get. That's about what we get. It's half of what we have. We have 44 students still officially enrolled in the class. There are 2 or 3 that I do not have anything from. So I know they're not participating. But we have 40 or 41 are, and that's a good number. And that's, you guys are hanging in there good. So give me that stuff. All right, let's see what else we've got here. And then we'll be, let you get to work. Lots of stuff turned in. I want lots of stuff turned in. I just love to grade stuff. Actually, I kind of do. So here's your Ohm's law exercise. That was your metric conversion exercise. This is your law exercise. And I think I only had, let's see. Oh, good. I've got a few problems here. Okay, not much. Okay, so Ohm's law exercises. And here, let's just see what this video is about. I don't recall. I should have looked at this yesterday, but I think this one is pretty good, though. 10 minutes. It's 10 minutes. We're not going to look at the whole, we're not going to look at it here. Just going to, but you should definitely do it. Okay, what have you got here? Why does it say?
So let's talk about the versus new way to launch your online course. So the first thing
Yeah, good for you. All right, it's 9 minutes and 59 seconds. Oh, okay. Well, this is the engineering mindset, which I really like. I really like it. I like his accent. I like the drawings. It's clear. This is primarily geared to electricians, but of course, what we're going to stick with us.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at Ohm's law to understand how it works as well as how to use it. There are also 2 problems at the end of this video for you to test your knowledge and see if you can solve. So what is Ohm's law?
Okay, again, by all means, look at that video. By all means, look at it. View the video and answer the questions below. And these questions here, these questions up through 12, refer to the video. So take a few notes as you're watching the video, relax, take a few notes, and then answer these questions. And you go right through that. Then over here, the formula. So you are taking third-year calculus, think you can get through this all right. And for those of you who have never can't spell calculus, I've always had trouble with that, even though I took it. Don't worry, you can't get any simpler than this. But remember to be working in the same units. It says how much current exists in a circuit with 50 volts and 2,000 ohms of resistance. I strongly urge you to draw out the circuit, make a little circuit. It's a simple circuit with a voltage source, a resistor, and a path for current to flow. Ask yourself, what am I trying to, what does he want me to do? What's this? Current. All right. So I put down I equals V divided by R over here somewhere. Write down the formula you're going to work with. Then start substituting values. Here you have to make, you don't make any changes. 50 divided by 2,000, bingo, you'll get the answer. Here you have milliamperes and 2.2 K. So I would, you want to, there is another way to do this, but I would suggest you change milliamperes to amperes and kilo to ohms. Do that and then do the math. 3, that's it. What the hell? Why did I give enough more? So here I'm asking you to find current, here I'm asking you to find volts, and here I do what this is. Ooh, it's hard. Okay, so you have 3 problems. I thought I gave you maybe 50. No, not really. But anyway, so you have 3 problems. Any questions about this? You know, get a cup of coffee, watch a 10-minute video, take a few notes, or I mean, you know, you can just look through the questions here, you know, halt the video, okay. You know, Ohm's law is a relationship between the 3 things, you know, write the 3 formulas down, you know, should be able to get through that without straining you. All right, let's look at the act. And again, this is just a short activity, but I want you to do this. Okay. So maybe we can open it. Wait. I never saw that before. We're also impatient. Wait. 22. Where? Okay. Where are you? Oops. Whoa. Well, let me get back here. Didn't like that. I'm not quite sure why that didn't open. Let's see. Okay, let's try that again. Okay, here it comes. Okay, 25 points, blah, 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 blah. So, you know, always look something over first. See, well, what's you got? 3 questions, 5 questions, reverse side, summarize, whatever. Okay. Activity. So it's an activity. That means you're going to make something. Construct this test to show that Ohm's law is valid. Proceed as follows. Okay. So you're going to use your solderless circuit board. You're going to place a 220 ohm resistor across a 9-volt battery and draw the circuit here. If you don't, for some reason, have a 220 ohm resistor, and you should actually have more than one, use something close and do the same thing. Do the calculation. So draw the schematic here, show a little block for your battery or a symbol for your battery, a resistor, and that's it. It's a simple circuit consisting of a battery, resistor, and a current flow. Using Ohm's law, calculate the current in the circuit. What did you get? So it's just, I equals V over R. You've got a V of 9 and an R of 220. Now, here's the key. I want you to use your meter, your digital multimeter, and I want you to use it to measure current. The problem with that is that it's kind of dangerous to measure current. Why is it dangerous? Because it's dangerous to the meter. You can blow out that fuse. So you have to be careful and just work this out carefully so you don't blow that fuse. Now open the circuit and insert the DMM set to measure milliamperes. All right. So you take your meter, you set it to measure milliamperes. Your black lead should be in the common jack, it always is. And your red lead should be where it says V, ohms, and milliampere jack. Okay, that's where it should be. Where is my meter? All right. But then you must open the circuit and insert the meter in that circuit as though it were like another resistor, like it was a resistor in series. Insert it in the circuit, not across it, but in it. Set the meter rotary switch to 200 M. That means it will measure up to 200 milliamperes. Now, using your two leads, measure the current in the circuit. In other words, you're inserting the meter into the circuit with your two leads. What did you get? And what you got should be very close to what you calculate. In this exercise or this activity, you're measuring current. You're using Ohm's law to determine the current in the circuit by calculating first and then by measuring. That's all you're asked to do here. Summarize your results. You don't have a variable power supply, so we really can't go through the other two factors. But this should work out. I mean, of course, you shouldn't have just read it and get the meter in this, break open the circuit, anywhere in the circuit. Stick the meter in, measure the current. So that's the work for this week. And again, I'd really like to see that stuff pouring in today, at least some of it. Metric unit conversion exercise. This is an exercise. This is an exercise. This is three things to do. 22. Are there any questions? Next week will be built. We're going to look at electronic components. There'll be a fair. I'll put this out. I'll publish it right now. We're going to look at electronic components. So we have a whole exercise that looks at the boards there, and then you're going to build this reaction timing tester. Don't dive into this yet, but you're going to solder this together, and we'll be into that. 7-segment display, switches on. All good. Any questions? Maria's here. Alexandria. Well, good. We seem to have our core 22. I hope the others are able to participate. I mean, I definitely get more work. Definitely get work from more than 22 students. But next semester, not that you care, this is going to be synchronous class. You'll be expected to be in a Zoom meeting. But that's. And how are you doing? Elmar, how are you doing?
Doing good.
Doing good.
Yes, sir.
And Joseph Gonzalez, how are you doing? Yes, you are. Let's see what you got here. Yeah, you're doing. You're all caught up, Joseph. Okay, and so most of you, and I'll be all right. So now I'm going to. I'll be getting off in a moment. I have a class at 9:30ish, and I will I will get your stuff graded today and tomorrow. Just check and you'll see.
Professor, quick question. This
Sure.
is Elmer.
Okay.
I think one of the first activities when you had us run just any LED through the 9-volt battery. I think that was in week 2. You sent in a message to Canvas like a couple days later. They kind of gave us like detailed instructions on all the components and exactly where we had to put them on the solderless breadboard.
Yeah.
Is there any way you can do something like that, or even if that's not possible, then maybe we can schedule like another call where we kind of do the activities together like we did today?
Mm-hmm. Well, there are a couple of things. Again, in terms of the board itself, the key is to understand how the board works and then work from the schematic drawing and put them where they will based on the schematic drawing. But if you want some help with that, that's sure. I'll be glad to do that.
Or even like maybe a little bit of extra practice on reading the schematics and even drawing out our own schematics, because I missed a couple calls the past couple weeks because I had to come into work. So even when I look at the schematics now, I'm a little lost, but I want to be able to understand like how to actually read it and put it together myself.
Right.
Instead of just following like, dummy instructions and put this here, put that there. I want to actually understand like the schematics.
Sure. And that's one of the key objectives of the course, to be able to read the schematic. And basically what we do is we have components that have certain symbols and we connect them with wires. And I try to start off with a very simple schematic, and we get a little bit more complicated as we go on further and further. And so you just don't learn to read a schematic all at once. You start off with something very simple like an LED in series with a resistor. And you look at the resistor symbol, you look at the LED symbol, and start to build from there. But the other issue that I think you're raising, and I'm fine with it. I don't know. I'm thinking of having maybe another. Well, first of all, you can contact me anytime. If you want to email me, as I said, you can email me 6 days a week, 8 to 8 o'clock. If you want to talk on the phone, we'll set up a time, and I can talk to you on the phone. And then if you want to separately, individually Zoom, we can do that. But I'm thinking of maybe having an open Zoom meeting like on Saturday. Would something like that work, where let's just say on Saturday at 10 o'clock, I'll throw it out. And
that would be great.
Would that be would Saturday be a good day for that? Because you're working, some of you are working during the week, of course, some of you I know are probably working on Saturday, but all right, so why don't I put that out here in an announcement? Why don't I say that on Saturday at 10 o'clock, we'll Zoom. I'll send everybody a Zoom message. You don't have to be there. If you're doing fine, that's fine. But it'll be just for anybody who has questions, and we can catch up. You want to do that? Does that sound?
Yeah, that sounds good to me. Yeah.
Let's try it. 10 a.m. Saturday Zoom. And if that time and day doesn't work out, we'll find another one. So yeah, I'm more than willing to do that. Okay. So, but again, if you want to contact me a little later today in an email and tell me what time you want to talk, we can just do a phone thing between now and Saturday. Well, this is Thursday, Friday, Saturday. Okay. All right, but we'll do that this Saturday. Saturday at 10 o'clock, we'll have an open Zoom for anybody who wants to. Okay?
Perfect, thank you.
Okay, any other questions or thoughts? Okay, if you haven't finished a week, by all that now, get done, go on into the 5th week. I'll grade your stuff. You'll get it back in the next, today and tomorrow. And I'll see you questions.
Oh, Professor.
Yes.
I got a question. For the multimeter,
Yes.
I accidentally left it on, and the battery got discharged. Do you know what type of battery the multimeter?
Yeah, I think it here. I'm looking at my one here. I think it's a 9-volt battery. You'll have to go in there. The 2 screws in the back and unscrew it. It doesn't have a little snap there. I'm surprised it ran down even with even if you leave it on. But you did. You left it on, and then it just.
Yeah, apparently I had left it on for like a few days because
Yeah.
I wasn't looking in my tool bag.
Yeah.
And,
Well,
it got discharged.
So what's happening now? You don't get any reading?
No, I moved the little.
No.
Hold on. Yeah.
Anywhere besides off, and you should get some kind of a reading, but you're not, huh?
No.
Okay, so I mean, it's not a problem.
Oh wait, I actually am.
Yeah, I'm surprised it would go down. These things don't draw much. So what do you get? So put it at 1,000 volts.
Oh, yeah, now it died again.
It died again. Okay. All right.
Yeah, it was giving me a little battery symbol, like on the.
Yeah. Okay. So open it up and see what's there. I think it's a 9-volt battery. I should know. I don't, but I'll open mine up.
My tools are outside.
Pop another 9-volt battery in. That'll happen. And watch that fuse. You've got a fuse in there. Hopefully you won't burn it out. If you do, you have to get another fuse. It's a bit of a
fuse. There's no fuse on there.
Yeah. Well, it's inside. Yeah.
Oh, I
get
get you. Okay.
No, there's no reason why you would have burned that fuse out. But be careful in measuring current with this, because you can do it if you don't break open the circuit. If you're not opening the circuit, you're doing something wrong.
Right.
To measure current. Okay, good. Any other questions? Okay, well, good. It's good to see all of you this morning, and have a good.
Thank you,
week.
Tom.
Okay, you're welcome. Thank you for saying that. That's I appreciate that.
This is the only interesting class I have out of my 2 classes.
Out of 2 classes, what's the other class?
English.
Oh, God help you.
I'm actually really good at English. I can't stand the subject.
But you're good at it, though.
Yeah. I was like reading and writing at the college level in elementary school.
Oh my. What is it? What English is it? 101?
Yeah.
101. I remember my English 101 at Valley College. I took English 28 and I got a C in it. Took English 28, which was prior to English 101, and I got a C in it. And I'm not bragging. I don't want to say, but if you go to my website, ronreese.com, you'll see all the books I've written. And I'm saying, hey, who knows what will happen? You know, my English teacher thought that, if I would write anything for publication, he'd laugh me out of the room. But you never know.
Right?
You never know.
Only time will tell.
Yeah, and all of that will help. Especially
Yeah.
maybe